Okay. Yeah, so this is based on some papers that I list here with some amazing co-authors, including many students. There are some blog posts on our blog which appear after some delay. And actually, I'll also mention a couple of papers that are just appearing on arXiv now. Okay, so let me explain the title. Is optimization the right language for understanding deep learning? And by optimization, I mean something very narrow, which is that there is some objective, f of theta, and theta is your parameters in the deep net, which you're training. And so you're trying to minimize it. And the other thing that optimization theory is interested in is to solve it as fast as possible. Okay, so that's the narrow definition of optimization that I'm talking about. And I'll argue that we'll have to go beyond that. Now, I want to explain this question by highlighting an old debate in neuroscience, which is, does the brain amount to optimization of an objective? I mean, these neurons have figured out some algorithm over the years, over evolution, and it's sitting in a vat of chemicals, and who knows what's going on. And are they optimizing an objective? And I emphasize that optimization means that once you've set an objective, you have to be ready to settle for any solution, right? So that's what optimization would mean. And that's still an open problem. But then for deep learning, people say, of course, there's an objective, right? It's written before you, the training objective. So of course, deep learning is just optimizing an objective. And I want to ask the question, is it? Okay, and my suggestion is that it's imperfectly captured by the value of the objective. And let me say what I mean by that and why that is. So there's an 800-pound gorilla in the room when you talk about deep learning, which is generalization, okay? And so as you've heard a couple of times today, today's deep nets are vastly over-parameterized. For instance, it makes sense to train a net with 50 million parameters and 50,000 training examples, or even 5,000 training examples, and it works okay. And generalization means that on held-out data, the ones you haven't seen, you still have low loss. So, which seems to fly against 1,000 years of philosophical tradition or more, Occam's razor that you should only trust simple solutions. You know, if you have a certain amount of observations, you should pick out the explanation that's simplest. And deep learning seems to violate that. And the traditional explanation, because people are so invested in or so absorbed in the optimization view, is that, well, there's a regularizer. Okay, so there's an objective f of x, and you regularize, which constrains the capacity of the model. So those 50 million parameters are not actually there. The regularizer is somehow taking care of them. Well, that comforting view was challenged by this well-known paper of Zhang et al. A couple of years ago, who showed experimentally that current deep nets are so over-parameterized that they can attain almost zero training error even on random data, randomly labeled data. Okay, so now on randomly labeled data, clearly there's no generalization, right? The future data you'll see will also be randomly labeled, and you'll never be able to predict those labels. And you know, these are using the standard training algorithms, the standard regularizers, etc. Still, this is true. So this shows that, you know, that overcapacity is there. It's not taken care of by the algorithm or the regularizer. And another easy implication is that, you know, by a simple change of this experiment, you can also check that the objective is gazillion minima, because you can take your data and add some randomly labeled data, and you can still fit that. Okay, so that shows you that there's just combinatorially large number, gazillions of minima, or almost minima. Okay, so that's really at the root of what I'm talking about. So, by the way, if there are more batteries for this, I think this is out of battery, if the staff have another battery. So the naive view of the objective is that it's like a score for a symphony. Okay, now of course we all know that score of a symphony is not quite 100% representative of the symphony, because the conductor and the players have some interpretation, but still it's largely in the score. And what I'm suggesting is actually maybe the objective that's written down is like a vague description of the symphony. Okay, it's got 4 movements. Here are the keys and tempo settings, and it ends with the choral part, which is the ode to joy. Okay, something vague like that, and that's not really enough to know what the symphony was. And so, how does the training actually happen? It's some algorithm. Okay, and we're talking about this objective, the vague objective that's written there. It's non-convex. It has multiple minima, as we saw. And in general, in this non-convex landscape, you make any tweak to the training algorithm. So you'll notice that I've stopped calling it optimization. I call it a training algorithm. You change the learning rate, add momentum, whatever. You'll, in general, have a different trajectory, and you'll end up with a different solution. And so I argue that it'll be these trajectory properties that determine generalization, the solution you get, and not the objective value, nor how fast the objective was made 0. And this observation, I tell it to the experts, and they say, yeah, we've known this. And so I say, well, the consequence is that it's not about optimizing the objective. So the TTI Chicago group has some lovely papers from which I learned a lot, including Surya, our session chair. And they have a lovely name for it called the implicit bias of gradient descent. And I want to say it's the implicit bias of the training algorithm. Okay, that it's a training algorithm that's determining, to a large part, the solution. All right, so before I proceed, I want to just remind you, most of you don't know this, don't need this reminder, about what I mean by traditional optimization. So there's this canonical analysis of first-order optimization. You saw it a little bit in Anima's talk. So this is gradient descent. And first order means that you're just using gradient information. And this is analyzed by imagining that there is a bound on the second derivative, the Hessian, which means that the gradient is sort of a reasonably stable quantity as you move around in the landscape. And so there's some upper bound on this, and then this thing which is negative is something that depends on the learning rate and the smoothness. Okay, and it's times the norm square of the gradient. And from that, you conclude that if the learning rate is small enough as a function of the smoothness, then the loss decreases at every step, unless the gradient becomes 0. Okay, so because you are in this non-convex setting, theory just settles for finding stationary points where the gradient is 0. Okay, there's no theory for getting to an optimum anyway. Another observation here is that this analysis, if you believe it, that this is what's happening, if you take a smaller learning rate, infinitesimally small learning rate, it should also work, just slower. But empirically in deep learning, you use a tiny learning rate, and actually it's much worse. Okay, so again, I point out all these things to my friends, and they say, oh yeah, we know this. And so that shows that this optimization story has something missing in it. All right, so the reason we're stuck with this view is because the loss is a black box, right? Some dozens of layers in the net, ImageNet data is just complicated. For mathematics, it's a black box. And so that's the way we think about it, about analyzing it. So it would be nice to get a less black box view, but how? And clearly we'll be using some simpler settings where we can analyze this. And so that's what we'll see in 3 separate vignettes in the rest of the talk. Vignette 1, training of infinitely wide deep nets. Okay, so wide means for a fully connected layer, you're imagining that the number of nodes in the layer goes to infinity. If it's a convolutional net, each convolutional filter has some channels. The number of channels is going to infinity. And this model came out of some physics considerations, a thermodynamic limit. There's in statistics a Gaussian process view of deep learning, where this also makes sense, an infinitely wide net. So there were these motivations, and that's why people started studying this. Now, in this infinite net, turns out, so the moral of the story is that gradient descent is going to find, out of this infinitely many solutions in infinitely wide net, something reasonable. Okay, and it has some surprising properties. Just to make sure you understand what I'm saying, here's a very simple data set. In fact, you'll see a study which it runs these infinite nets on these small data sets. So there's a classic UCI data set, which data sets which people used to use 10, 20 years ago. So this is one problem in it, multi-class classification, 17-dimensional input. These are tiny data sets, 339 training samples. All right, we're going to train a fully connected 5-layer deep net on it. All right. And it's infinitely wide, okay? So it's 5 layers like this, and these layers are going to infinity. So it's some kind of a mathematical limit that you're going to initialize with suitably scaled Gaussians, all of these layers, so that the expected node value is equal, okay? So it's some scaling, and then this all makes sense. And the question is there a limit? As you train this infinitely wide net, is there a limit that emerges? And so now you're thinking, okay, this is too expressive. It'll overfit the training data, because if you remember the representation theorem for neural nets, you'll remember that even if you have 2 layers and an infinitely wide middle layer, you can represent any function of any finite function. So therefore, that shows that the number of zero-loss solutions goes to infinity. So it's infeasible to train as well. So, what is the point of studying these questions, right? That's what you're wondering. Well, here's, for that simple data set, here's what happens. You train an infinitely wide net, and the test accuracy is 51.5, okay? And on these small data sets, there were these old champions like RBF kernel, random forest, and it's better than that. Okay? So now in the next couple of slides, I'll tell you a little bit about how this can be done, okay? That you can get this number, the exact number. And this has to do with what's called neural tangent kernel, or NTK, and there's a convolutional analog for this. And the main theorem says the following, that the following are equivalent for any finite data set. You take an infinitely wide neural net or convolutional net and train it with infinitesimally small learning rate with gradient descent. So that's one thing. And on the other side is you're going to do kernel L2 regression, simple old algorithm, with respect to this neural tangent kernel. These two are equivalent, okay? So in the infinite limit, as you make the width infinitely large, the neural net training converges to L2 regression with respect to this new kernel. And then in this paper upcoming NeurIPS, we gave an efficient and GPU-friendly algorithm for computing the convolutional analog of the NTK. Okay, and so if you can compute the kernel, you can actually compute exactly what the infinite net is going to do on any finite data set. So that's what you get. Okay, so that's how these results were done. So just a glimpse of the details. In more mathematical notation, you have, this is just for fully connected nets. You have a bunch of layers, L layers. The activation is sigma. It works for any activations. The entries are standardized as Gaussians. Layer weights are going to infinity. You're training the network with square loss, regression. And if you compute what that does, the square loss, it basically involves this kind of dynamics where the output is changing according to this expression, some matrix times the difference between the current output and the labels. So this is just a vector y of all the labels and of all the data points. So this is a vector on the left, vector on the right. And this matrix Hij is a kernel matrix, which is this thing. And I'll say a little bit more about this on the next slide. And that's the theorem, that as width goes to infinity, this evolution equation, the h in that approaches the limit h star, which is the neural tangent kernel. Okay? Infinitely wide nets are definable multiple ways. You know, this has L2 loss, arbitrarily small learning rate, etc. Not all of them will reduce to NTK regression. And the proof, as you can imagine, is some kind of induction on depth, and you have to estimate how much the parameters are changing so that, you know, this initial description in terms of the h is still valid as the training proceeds. Just to unpack the previous slide a little bit. So what am I saying? So remember, what I'm talking about is kernel linear regression. And there's this old idea in machine learning, which is that instead of doing regression, the simplest machine learning algorithm, on the input x, you're going to do it on some representation of the input. And the representation is in this reproducing kernel Hilbert space. It could be infinitely long. So it's some mapping phi, which maps x to some high-dimensional vector phi of x. And these are some popular kernels. And the kernel trick says that if you want to do regression on this much higher dimensional input, phi of x, that's possible provided you can just compute the inner products of phi of x for different inputs. So that's the kernel trick. And so the neural tangent kernel is some new kernel, this mapping from input to some other representation. And each coordinate of phi of x corresponds to a parameter w in the net. So the number of parameters is going to infinity. This is infinitely long. And the corresponding entry is the partial derivative of the output with respect to that particular parameter. So it's some infinitely long representation of the input. And so the dynamic programming algorithm allows you to compute these inner products. Okay, so that's why neural tangent kernels are tractable. So you can think of it as some kind of a compressed view of the infinitely wide net. All right, so what good are these? So as I mentioned, you run them on small data sets. So the reason you run them on small data sets is because it's, kernel SVMs, supposedly a classic algorithm and all that, actually is quadratic time in the number of training samples. So you cannot run it on ImageNet. Okay, that's the problem. But yeah, you can run it on smaller data sets. And so the first one I'll mention is this UCI data sets, which have been studied a lot. And there, the classic algorithm was random forest, boosted decision trees. And actually, NTK beats it right off the bat. Okay, and all the scores we tracked. Then there's another manuscript with the same set of authors where we have a testing of the convolutional version of NTK. And there we find that it rivals AlexNet, okay, the original deep net that got attention on CFAR10. So it gets 89% on CFAR10. And this is the best kernel that was not trained on the data. And the architecture involves the CNTK with average local pooling, which is something we introduced, which is a kind of way to incorporate data augmentation. Many of you know about data augmentation, and that's just very difficult with kernel methods because if you increase the data, there's a quadratic penalty in the running time, and this has data augmentation built in. All right, so these kernels work pretty well on these smaller data sets, so they generalize very well. Infinitely wide net on a small data set, it generalizes pretty well. And to understand this generalization, we just have to understand why kernels generalize. So you should go to Misha Belkin's talk in a couple of days, which is also about these topics. So that was vignette 1, changing gears completely. Another simple setting, we're going to study how to solve matrix completion via deep linear net. Okay, matrix completion as in the Netflix challenge, which those of you old enough to remember this from 12, 13 years ago, that Netflix wanted a prediction algorithm for what movies you like, and that you think of it as a large matrix, users times movies, and users rate a few movies, so those are some entries of this matrix that are revealed, and you're trying to predict the remaining entries. Okay, so this we'll do with deep learning. And again, gradient descent is going to have a powerful effect on how the solution is obtained. And exactly formalizing that effect will be very tricky, as you'll see. So gradient descent has magical properties, but we don't know how to capture it mathematically. So matrix completion, formally, mathematically speaking, is just there's a low-rank matrix, unknown, M, n by n. Entries are revealed, so rank is R. Entries are revealed in a random subset of locations, omega, and your goal is to recover the matrix. And this classic algorithm by Srebro et al. Is a convex programming algorithm. We are trying to find the matrix which, in the least square sense, best fits the entries that have been revealed. So M is a matrix, Mij has to fit entry Bij, which was revealed. And you're trying to fit a matrix with the smallest nuclear norm. So that's kind of like a regularization term. And the nuclear norm is the sum of the singular values of the matrix. And the sum of the singular values is some kind of a proxy for low rank. Okay, if that's small, the rank is small. And there were some celebrated papers culminating in Candace and Rath, which showed that this algorithm is statistically optimal. Meaning it's the best possible algorithm given a certain number of entries that have been revealed. And I put the optimal in scare quotes because, as you'll see, that's not the case. It's not completely optimal. All right, so Gunasekar et al., Surya, who is the session chair, their paper had a very nice idea, which was, let's forget about the regularizer and just trying to find this unknown matrix as a product of two n by n matrices. No rank constraint, just general n by n matrices. Okay, and just do a least square fit. Now you look at it and you say, wait, clearly there's lots of, it's underdetermined, there are lots of solutions, right? Infinitely many solutions. All possible matrices are solutions, potentially. And there are many of them which fit the observed entries. But somehow, empirically, they found that gradient descent finds solutions that works as well as the nuclear norm minimization. You completely forget about this regularizer, which promotes low rank, and just gradient descent itself has this effect. And so they suggested that gradient descent in this setting has in the background this ghost regularizer, which is like the nuclear norm. Okay, just in the process of doing gradient descent on this very simple problem, in the background, gradient descent is imposing this ghost regularizer, which is the nuclear norm. So that was their conjecture. All right. So as you can see it coming, turns out there's something else going on, something more going on. So, and which emerges when you do 3 layers instead of 2. So this is a deep linear net, and this is our paper with Nadav Cohen, Wei Hu, and Yuping Luo. So you use n layers in this. So you're multiplying n matrices instead of 2, and just doing least square fit to the observed entries. And now this is like the deep learning philosophy taken to an extreme. You just forget about the domain knowledge, which in this case is that the matrix has to be in low norm. You just forget about it, and you're just taking the product of n matrices and just hoping that gradient descent will do something reasonable. By the way, this is exactly, it can be solved by backprop. It's exactly a subcase of deep learning, and checking how well it does on the held out locations that you haven't seen is exactly like generalization. So this is really a question about generalization of linear nets. And so good news 1, it actually solves matrix completion even better than depth 2. Okay, depth 2 for a certain number of revealed locations has that error, and depth 3 has several orders of magnitude better reconstruction error, and depth 4 is just slightly better. Second good news, that you can do some mathematical analysis. So, this deep linear net, when it's trained by gradient descent is working in some non-convex landscape, and you can analyze how this end-to-end matrix is evolving, and in particular, its singular values and singular matrices, singular vectors. And this dynamic evolution shows that there's a rich get richer phenomenon, that a few large singular directions start dominating, and which promotes low rank. So it's a sort of qualitative theory, which you get out of this. And the interpretation is that the goal of the gradient descent is to make singular vectors of M align with those of the loss, and the singular directions grow one by one, not all at once. And indeed, in the experiments, you see that there's a big difference between 2 and 3, depth 2 and 3. The depth 2 sort of grows all the singular directions roughly together, but depth 3 shoots up singular directions one by one. So it's doing a very different thing. And the math is suggesting that. All right, other news, evidence that the Gunasekar et al. Conjecture is false. Sorry, Surya, but she knows this. She's seen this paper. Adam optimizes much faster than gradient descent, so you can use a different training algorithm. Again, I don't call it an optimization algorithm. Use a different training algorithm, and it gets to zero error much faster on the training, but it generalizes worse. Okay? And there's some evidence in the paper that this gradient descent trajectory may not have any simple characterization in terms of usual matrix norms, like nuclear norm. So that was that paper. So this is just showing you that, yes, gradient descent in this deep setting has magical properties, but how exactly to capture it or relate it to things we already understand, like matrix norms, is not easy. Okay, vignette 3. an exponential learning rate schedule in deep learning. And this is joint work with Jian Li, and it should be on archive tomorrow, I hope. And Jian is also giving a spotlight talk and poster on Friday. All right, so learning rate in traditional optimization. So I started with some reminder about how analysis optimization works, this simple update. And in deep learning, the standard schedule is that you start with a high learning rate, and then you gradually, in a few phases, reduce it. And you decay this learning rate over time. And there's some literature in optimization that justifies this kind of thing, that even in the case of convex optimization, if you keep the learning rate high, it starts bouncing around towards the end. It never settles into the optimum, and so you may need to decay the learning rate later on. So that's the traditional wisdom. And I must say that within the last couple of years, there have been some experimental work which suggests that there's some crazy stuff going on underneath the covers. That actually there are these crazy learning rate schedules. Shoot up the learning rate, drop it, shoot it up, things like that. And nobody was very clear on what's going on, like why that works. Well, let me muddy up the waters even more. Okay? So result one, empirical. I mean, obviously, we did the theory first and then the empirics, but let me tell you the empirical result. It's possible to train today's deep net architectures, the state-of-the-art ones, while growing the learning rate exponentially. Namely, at every iteration, you're multiplying the learning rate by 1 plus c for some c bigger than 0. Now, all of you know about exponential growth. So what this is saying is you're making the step size larger and larger exponentially until it reaches millions or billions. We need 32 bits of precision to keep it. Okay, it's very large. The optimization is making huge steps, and it works. Okay. So that's the empirical. Why did we ever think of such a crazy idea? Well, because there was this theory, a mathematical proof that our schedule is equivalent to existing training schedules. And what's the asterisk? It's in all the nets that use batch norm or any other suitable layer normalization scheme. And there's this idea of Joffe and Szegedy, which is you introduce some kind of a normalization layer at every layer of a deep net. And this is used basically in all architectures today. And when you use batch norm, then you get this phenomenon with the current schedules. That the current schedules are equivalent to something like that. Okay, so batch norm is just a fact of life, and so nobody even thinks of commenting that a network is using batch norm. It's part of training. All right, so let me tell you the formal statement. So the general training algorithm for deep learning today uses, it's first order, so it's using the gradient. But it also has something called momentum. So there's this other variable vt, which is capturing the momentum. And so there's a momentum rate gamma, there's a gradient, and there's something called weight decay, which is a regularizer. Okay? Because it's called a weight decay because when you take the gradient, it's basically like knocking down the scale of the parameters at every step. And people think of it as, the regularizer is promoting generalization, at least that's the loose phrasing, and momentum and learning rate have to do with optimization. But again, as I've been suggesting in this talk, it's all mixed up, right? Optimization and generalization are mixed up. And indeed, there is a way to get rid of the weight decay completely and get this exponential learning rate. So the following is equivalent to about for the nets with batch normalization. You make the weight decay 0, keep the momentum the same, and use a learning rate schedule which is exponentially growing. So alpha is less than 1. So the learning rate at time t is some initial learning rate times this exponential function of the time. And alpha is a non-zero root of this equation. And for the standard values of learning rate and weight decay, and gamma, this has real valued learning rates, and so this translation to an exponential rate schedule works. The proof uses a trajectory-based analysis, which is my general point that you should not view the objective as this black box, and that you only have access to its gradient or its Hessian norm. That you should keep track of what's going on to the parameters during this training, and the proof uses that very heavily. Another thing it uses is a property of batch norm, which I forgot to say. That batch norm, because it normalizes the layers, has this buffering effect that increasing the norm of the layers doesn't have any effect on the loss. So use those properties to prove this theorem. Okay, another interesting phenomenon I didn't talk about, but Ron-Gil's talk addressed this morning, mode connectivity, which again is in line with this philosophy I've been saying, that there's magical stuff happening along the trajectory of gradient descent or stochastic gradient descent. And one of the magical things that happens is that these solutions found by gradient descent have the property that they can be connected via these piecewise linear paths in the landscape where the loss is low along the entire path. This is again a property of solutions that only of solutions that are found by training algorithms, not all solutions in the landscape. Okay, so conclusions. There's a need to rethink machine learning theory for non-convex models, and trajectory seems key because different trajectories on the same objective lead to different generalization, which is what we're interested in. And we need to learn vocabulary for discussing trajectories from physics, dynamical systems, PDEs, etc. And there's a special year in machine learning optimization, statistics, etc. Here at the IAS this year. And those of you who found your interest in deep learning whetted by this workshop, please come visit. And we are very interested in some of these questions. Thank you very much.